So we're moving on to cylindrical coordinates, which is still triple integrals, but we're going to try to do some of those integrals that would have been kind of tough to do in regular triple integral rectangular coordinates, but would turn out to be a little bit easier if they were done in a new coordinate system like cylindrical coordinates. And if you notice, cylindrical coordinates is just like polar coordinates, except it's in 3 dimensions. And the z is equal to z just tells us that we're really in 3 variables. So if we imagine ourselves in polar coordinates and then doing stuff in 3 dimensions, then that's really what cylindrical coordinates is. Now, when we change coordinates, remember this thing called the Jacobian, and that's the integral change that we need to replace our differential, our dx dy or dy dx, also known as our dA, and now we're going to do it with 3 variables. Yeah? No, that's okay.
So do Jacobian transformations for 3 variables simultaneously?
Probably not 3 variables, maybe 2.
Well, I mean, 2.
Yeah. Yeah, so maybe we'll do it. The last section in this chapter is called the official change of variables section. And that's when we actually take a look at the differential, and we'll look at it in 2 dimensions and in 3 dimensions. Yeah, so Jacobian for this is going to involve 3 variables, and so you would imagine that your Jacobian will have 3 parts to it. So remember how we write the Jacobian was the partial of x, y, and z with respect to the 3 variables that are new variables that are going to be involved. And so r and theta were what we had for polar coordinates, and then we had z is equal to z. And so I'll write out symbolically what this is going to look like. It's function x. And I'll use, instead of the partials, I'll just use a subscript notation. So we're looking at the function x with respect to the first variable r, and then the same function x with respect to the second variable theta, and then the same function x with respect to the last variable z. And then we would have y's next, and then we have z last. So if we look at the functions up here and take the derivative with respect, take the derivative of the function x with respect to r, that's just going to be cosine theta. Take the derivative of x with respect to theta, I think that's negative r sine theta. And take the derivative of x with respect to z, well, there's no z's in there, so that derivative is just going to be equal to 0. And then now with y's, take the derivative of y with respect to r, take the derivative of y with respect to theta, take the derivative of y with respect to z. Again, there's no z's in there, so that's going to be 0. Finally, take the derivative of z with respect to r, take the derivative of z with respect to theta, and then take the derivative of z with respect to z. It's just 1. So we have a 3 by 3 matrix for which we're trying to find a determinant, and there's a row or a column full of zeros. And so I know we haven't talked much about determinant, and we'll just say determinants aren't really that important here as long as you know the calculations for certain things like the cross product, and I don't know what else we did a determinant for. But for this one of the ways to find determinants is to expand on a particular row or column, they call it. And so we can think about each of these elements as having a sign assigned to it, so that when we expand on that particular element in the matrix, we would give it a sign. And we did that, I don't know, knowingly or unknowingly. We did that for the cross product. Remember, the J always had a negative? And so these signs essentially alternate for each of these elements or each of these positions. And what we would do is we would say we would expand on a row or a column with the given signs. And so I like the column, the last column or the last row that's full of zeros. And so let's say we're expanding on the last row. And so the way to compute this matrix is to take that first element in the last row and assign a positive to it. It's 0, so whatever is going to come next won't matter because you're going to multiply it by 0. But technically, you would multiply this by whatever this submatrix is after you cross out the row and column that this element is in. So I would cross out that last row, and I would cross out that last column, and then I would have this matrix left: negative r sine theta, 0, r cosine theta, 0, and 0, and 1. So that's how we would approach doing the determinant. Now, like I said, it doesn't matter what happens in here. We have, I'm sorry, this last one shouldn't be there. Because we're left with a 2 by 2 matrix. So 2 rows and 2 columns, and then it's not going to matter what goes in here because this is going to be multiplied by 0. Similarly, when we expand along the second element, I would have 0 here again with a negative, and then whatever is left over up on top. And so that's a cosine theta, and a 0, sine theta, and a 0. Again, that's going to be 0. What will matter is this last one, and that last term is going to be multiplied by 1. And we have a 2 by 2 matrix with cosine theta minus r sine theta, r cosine theta. And then now we have to find the determinant of this 2 by 2 matrix, which is just the product of the diagonals minus the product of the wings, the other ones. And so we have r cosine squared theta minus negative r sine squared theta, which is r times sine squared plus cosine squared, which is just going to be r, which happens to be the same as our polar coordinate transformation. Okay, so that's the Jacobian work to make our transformation from dx, dy, dz, or I think we kind of combine it together and call it d capital V. Okay. So let's take a look at how the triple integral will change. So we have to imagine that we're looking at some solid in 3 dimensions that maybe would have a form of a cylinder or cylinder-like, or something that's kind of polar coordinate-like that's gone up. And then this is going to get changed into a triple integral over, we'll call it E star to say this is going to be a new volume. And if it is in fact cylindrical shape with, circular cylinder, then we should expect this to be constant limits. So we're going to make our transformation changes in our function. Instead of x, y, z, we're going to replace x with r cosine theta. We're going to replace y with r sine theta. And then we're going to just keep z as a z. So now our differential that used to be dx, dy, dz in some sort of combination or permutation of those 3 things will end up being dr, d theta, dz. But remember that there is an extra r that pops up from our Jacobian. And then how we're going to integrate with respect to first will depend on how we set up our integrals, or how our E star turns out. If it's constant, well, it doesn't really matter which way we're going to integrate first, but sometimes you might have some functions involved, and most of the time, yeah, it's not. There you go. There's going to be some cases where something is going to be a function of something else, in which case we'll have to be careful about the order of integration. But like I said, if this is in the shape of a cylinder to begin with in E, then when we change it to E star, it'll end up being constant limits. And we'll see some simple examples of that. Okay? So, I guess let's just do some examples now. And now we also have some basic idea about triple integrals and its application, so we're not just stuck with figuring out hypervolumes or something like that. We could be looking at center of mass or whatever else you guys might have had in your homework. So here's one of them. Let's see if we could do this this first one up on top here. This one's asking us to evaluate this triple integral where we have x squared plus y squared inside of the integrand. And E is a region that lies inside of the cylinder, x squared plus y squared is equal to 1, between z is equal to 3 and z is equal to 13. And what we want to do, like always, is try to visualize this thing. now that we're going into 3 dimensions and cylindrical coordinates, it would be kind of helpful if you can see what this E looks like. So it's a cylinder, but it got chopped off at 3 and 13, so Z is equal to 3 to Z is equal to 13. So it'll be that portion of the cylinder. And if you can see it in 3 dimensions, you can imagine what the R and theta is going to look like in 3 dimensions. And if you can't see it in 3 dimensions, then I highly encourage you to draw it in 2 dimensions. Just draw the shadow that this is going to make on the XY plane. And the shadow that it's going to make on the XY plane is simply a circle. Looks like it's going to have radius 1. And so that's going to give us our R and theta. And the Z's were just constant horizontal planes, and so they're just going to be constants as well. So imagine trying to do this in Cartesian coordinates and rectangular coordinates, which I wouldn't necessarily advise, but it can be done. So let's start with that. In rectangular coordinates, we would integrate this probably want to integrate it with respect to Z first. I guess it doesn't really matter, but if we integrate with respect to Z first, I would go from 3 to 13. And if I were to integrate with respect to X and Y, this is a circle, and so I'm going to have functions involved here. And let's say I'll integrate with respect to y first, and I would go into a negative square root of 1 minus x squared to positive 1 minus x squared. And I'm not doing this in limits. I'm not writing out the inequalities like I would normally, because this is not how I'm interested in doing it. I'm just giving you an example of what's happening, or how difficult this would look like if you did this in rectangular coordinates. So the outer limits are always going to be constants, and that's just going to go from minus 1 to 1. All right, and looking at this integral, I don't know how easy it was to set up for you, but it wasn't too bad. But now, in terms of trying to integrate this, it's going to be difficult. All right, now let's do this in cylindrical. And in cylindrical coordinates, a lot of times we're going to want to integrate with respect to Z first, because Z kind of gives us the function, and then the R and theta kind of give us our domain. So it's essentially polar coordinates. Very special cases where it might not be polar coordinates, some other weird things that could happen. But if we treat this like it was in polar coordinates, this is how it's going to go. So we got Z going to go from 3 to 13, just because the constants look like that. And then now we have R and theta based on the 2-dimensional drawing that you drew. It looks like it's just going to go from 0 to 1 for R, and then theta goes all the way to pi. And so there you have all constant limits. And not only that, the x squared plus y squared is going to become r squared. Even better. So we can start by writing this as a square root of x squared plus y squared, but x squared plus y squared is equal to r squared, so you can write it as square root of r squared, which is just r. And then you would multiply this by the extra r from the differential, from the Jacobian. And then now you figure out, well, in this case it doesn't really matter, does it? Because you can do it any order you want. We have just single variable in here in the integrand, and we have constant limits. So it doesn't really matter how we're going to integrate it. So let's integrate with respect to z in the order that we wrote it, 3 to 13, with respect to r from 0 to 1, and then with respect to theta from 0 to 2 pi. And now in general, I don't really like doing integrals in class anymore, but this one is so easy that I can't really help it. Let's just do it. Because it's constant limits, and because the integrand is something that can be, factored around, taken out, or whatever, you can really just split it up into 3 different subintegrals. And the hardest one is integrating r squared. So what do we have? We have 2 pi for the first one. We have 1/3, right? R cubed over 3, evaluated at 1 and 0. And then we have 13 minus 3. Okay. Any questions? That was kind of fun. Let's do another problem. Let's do another problem. Let's check our answer. Let's do number 15. Looks interesting. So remember, when we're using triple integrals, cylindrical coordinates is in triple integrals. When we use triple integrals to find the volume, the integrand is going to be 1. Find the volume of the solid that is enclosed by the cone in the sphere. So the first thing we should think about is that the volume of E is going to be equal to the triple integral over E of 1 dV. And so for us, the really big challenge is to try to write this in terms of cylindrical coordinates, just find the limits. So now we have a cone, x squared plus y squared is equal to z squared. Remember that? That's 2 cones, and then if you just take the positive part of the square root, you just get the top half, top part of the cone. And then you have a cylinder, or not a cylinder, but a sphere with a big radius. So it looks like you're looking for this piece of the cone and the sphere taken out. So you're doing this in cylindrical coordinates, which means if you integrate with respect to x or z first, you would draw a line parallel to the z-axis, and you would ask yourself, what z function are you going to get into? And then you'll be inside of the region, and then you're going to get out what z function are you going to get out of. So you're going to enter through the cone, and we probably should start, since we're going to go into cylindrical coordinates, we probably should start looking at this in cylindrical coordinates. And so how would you write this in cylindrical coordinates? Square root of r? Square root of r squared, right? Which is just r. And then you'll get out of this region by looking at z is equal to the sphere, solve for z, and it's the top half of the sphere, so it's a positive 98 minus x squared minus y squared, which can be rewritten in spherical coordinate, cylindrical coordinates. (98 minus r squared). Okay? So those will be our z limits. Lower limit at r, upper limit at 98 minus r squared. And so we see now that we're not always going to have constant limits, especially if your E region is not shaped like a cylinder. Here it's a cone. Okay? Now the other tricky part is to see what happens in the shadow of the xy plane, because that's how cylindrical coordinates work, is that we're going to need to integrate over the shadow of the xy plane. And so on that shadow of the xy plane, that's how we're going to create our r and theta. So let's bring ourselves back to the xy plane and imagine what the shadow of the xy plane is going to look like. Well, if you project the light directly above it, we'll see a circle or a disk. Now the question is, what is the radius? That's going to give us our r limits. Now just set up our r and theta limits. We know that r is going to go from 0 to whatever the radius is, and theta is going to go all the way around from 0 to 2 pi. So the question is, what is our r limits? Any ideas on how to find that? Plug z into the sphere. Okay, so we'll plug z into the sphere, and then we're going to get an equation with an x squared plus y squared is equal to some new radius that we're going to find. So we got x squared plus y squared plus z squared equals 98, and the z is equal to the square root of x squared plus y squared. So you take the square root, or you take the square of a square root, and I'm just going to give you 2x squared plus 2y squared, and half of 98 is, what is it, 49? And then we want to look at this as the square root, or as a square of something, right? So we want to take the square root of 49. I think that's just 7. So that's going to give us our radius. And that's essentially what r is going to be, or at least the top limit of r. Okay? Yes?
Why did we plug in the equation of the cone into the sphere?
Because we're finding the intersection of the cone and the sphere, and that intersection brought down to the xy plane will give us our region that we're integrating over. And so we have to find a way to set them equal to each other somehow.
And that's the intersection between the sphere
And the cone, correct. All right, aside from the z, the last two limits will be constant limits, so that's nice. So we can go ahead and set up our integral now. And our integrand is 1, but when we change our dv into dz, dr, d theta, we're going to have an extra r coming out. And then we're going to want to integrate, definitely want to integrate the z first, because it's a function of, the limits are functions of r, so we want to integrate the z before we integrate the r. So dz, z goes from r to square root of 98 minus r squared. And then at this point, it doesn't matter which way we integrate, but let's do r second, going from 0 to 7, and then theta going from 0 to 2 pi. Okay. Now, we don't have any thetas in our integrand. We do have an r, and we also have z as a function of r. But since we don't have any thetas, we can actually not make full use of that Cavalieri's principle, but we can at least take out the theta, or take out whatever's inside of the theta, because it's constant with respect to theta. And then we're kind of left with a double integral. Okay. Now this integral is manageable. The first integral, the inner integral, is z. So you're going to say z evaluated at 98, a square root of 98 minus r squared minus r, and then you multiply that by r, and then that should be doable integrals. Okay, I'm going to have to trust that you guys can do these integrals that don't require anything fancy. They don't require integration by parts or partial fractions or trig substitutions. You should be able to do a u substitution integral. And that's what's going to happen here eventually. All right. I'll put a dot, 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 and let's move on. Any questions? Aside from, can you integrate that integral, please? Okay. So we can do another one, but let's do this one where you don't have the volume. I mean, they don't tell you explicitly what the E solid region is. They just give you an integral and they expect you to figure it out from there. So let's do either 18 or 19. Any preference between these two? It's smaller, huh? Does it look smaller? Yeah. All right, just pick a number, 18 or 19. 19. So they want us to evaluate the integral by changing into cylindrical coordinates. I don't know, it might be possible to do it here this way directly, but it'll be kind of difficult. So let's see if we can change into a different coordinate system. So what we essentially want to do is kind of work backwards. Instead of giving the region and then us trying to find the limits of integration, we're going to extract the region from the limits of integration. And so if I write this in the order that it's written, z, y, and then x, that's going to help me find my region. And if I look at z looks like it's going to go from 0 to 4 minus x squared minus y squared. So I'm going to need to know how some of these things look like. Z is equal to 0 is a plane, the xy plane. Z is equal to this thing is a try again. Just a paraboloid. It's a circular. It's going to end up looking like a circular paraboloid. Okay. Let's take a look at it right now. Z is equal. This is what you want to get. If this is a little too hard to look at, maybe you can extract it and write it as an equation. Z is equal to 4 minus x squared minus y squared. Now, back to the quadratic equations. Remember I said you should try to memorize it, and then I didn't put it on a test. And I don't know how many of you guys actually tried to memorize it. But don't forget it, because it's going to come back. So I have z is equal to, I have a z, and then I have an x and a y. The x and y are both squared. Z is not. So already I should be looking at this as being a paraboloid. Now, is it a paraboloid like a cup, or is it a paraboloid like a saddle? I look at the signs for the x and the y. They're both the same. So it's going to be like a cup. Now, they're both negative, so it looks like it's turned upside down. And then there's a 4 in it, so it looks like it's been moved up 4 units. Okay? So it's an upside down paraboloid up 4 units. And it's probably going to intersect the xy plane. If you imagine z is equal to 0, it's going to intersect the xy plane on a circle that has radius 2. Okay, so y goes from 0 to the square root of 4 minus x squared. Now y is equal to 0, we know what that is, right? What is that? Before I say we know what that is. Well, x is going to go from -2 to 2. So, but the y is equal to 0 is what? Oh, let's look at it in 2 dimensions, because we've taken care of the z as a 3rd dimension. So in 2 dimensions, y equals 0 is it's the x-axis, right? So the boundary is going to be the x-axis. And then goes from -2 to 2. X goes from -2 to 2. Can you picture what this would look like in 2 dimensions? Yeah?
It would be the top half of the circle from the x region to -2. It'd be the top half of it.
So the whole top half of the circle. All right, so we'll do this, and then I'm going to save some space to actually draw this region over here. So on the xy plane, we have the top half of the circle. Of radius 2. It's trickier when it's one of the sides, left side or the right side of the circle, which could happen sometimes, and so watch out for that. Now back to this 3-dimensional picture, we have an upside down paraboloid it goes to 4. Not that 4 matters, because that's just part of the equation. And then now, if we take a look at how this is cut in half, it's the top half of the circle, so that's on the y-axis, the positive y-axis. So positive y-axis. So it looks like it's this. So it's just one side of this paraboloid, right? It's the side of the paraboloid that's on the positive y-axis. All right, so now that we have a general idea of the shape, let's see if we can translate that into cylindrical coordinates. I think maybe about 85 to 90% of the time you're going to be writing your cylindrical coordinate limits with a z first and then the r and the theta. So our z is going to go from 0 to this thing, which is the paraboloid. Well, if you just remember x squared plus y squared is equal to r squared, we can write this paraboloid with 4 minus r squared. And once you got the three-dimensional portion of it out of the way, we look at our two-dimensional portion with r and theta. The radius just goes from 0 to 2, and then the angle goes from 0 to pi. Okay? The only other thing to worry about is the integrand. It's just the square root of x squared plus y squared, which is r. And then the dz, dy, dx translates to r, dz, dr, d theta. So now we can write our integral. So the r comes from here, and then another r is going to come with the differential. Then we have dz. Z goes from 0 to 4 minus r squared. dr, which is going to go from 0 to 2, and d theta going from 0 to pi. Okay? So this is manageable. Any questions? Yeah.
How to determine the order by which the integration is?
In general, you want z first. Now, in this case, it doesn't matter the order, except that the z has an r in it. So you're going to have to integrate z inside of integrating with r. And then the theta doesn't matter, because there's no thetas in here in the integrand or in the limits. So thetas don't matter.
So theta was there somehow. Could we just split the theta integral, like take the theta integral out and just have the double integral?
Yeah. Just like last time, we could take the theta integral out. And that already, is pi. Let's integrate that. It's just going to be theta from 0 to pi. So Whatever that double integral is, you just multiply by pi, and then that's it. Okay? All right, so you need to be able to read a triple integral and extract the solid out of it so that you can change a coordinate system if you have to. Any questions? Yeah. Yeah, you could really just substitute. I think figuring out what happens in the two-dimensional case, the x and the y, is important because that's you need to try to see what part of the circle or what part of some region you need to integrate. But since this is really a direct translation from x squared plus y squared into r squared, you don't really need to see the three-dimensional picture. But I do believe that you still need to capture the two-dimensional picture so that you can do the proper translation. Okay? All right. How about those intersecting cylinders? So let's try to find the volume of two intersecting cylinders and see. Now the extra credit was the surface area, right? For those people that did the extra credit. Yeah? Wasn't it? There's absolutely no response. Like, you guys didn't do. I see a stack of paper there. Somebody must have done the extra credit. Was it the volume or the surface area? Anybody remember? Did you guys skip that problem? No? You're not gonna tell me? I was in Washington, D.C., and I was in the subway system. It's a cool, it's actually two intersecting cylinders that you know, the subway. Yeah, I have a picture of it, but I forgot to get it ready. Well, yeah, it's not two trains going. It's not two railroads. It's just the tubes themselves are intersecting, but there's the actual train goes in one cylinder, and then the people going in and out go from the other cylinder. Yeah, I don't. So we can pick any two cylinders. If we imagine the cylinders intersecting at the origin, there's actually three cylinders, but we could just pick any two of them. And I think I have a drawing of it, two cylinders here. So I have x squared plus y squared is equal to 1 is one cylinder, and y squared plus z squared is equal to 1 is the other cylinder. And so this is how it would look like initially, but of course we don't want to see the extension of the cylinder. It would be really interesting to see what happens to take a look at just the cylinders themselves. So let's get a picture of this because it looks cool. But the real picture that we should probably focus on is the actual intersection And the actual intersection kind of looks like this. I need to change one of the colors. Where's the other red one? There he goes. Oh, that didn't help. I don't know if that's useful. A color change. Oh, maybe I should make it yellow or something. That's a little better. So the key idea is that we're going to want to look at the top part of this. Well, first of all, if we just look at cut it in half, if we cut it in half, then we could just double our volume. So we'll take advantage of symmetry and just take the top half of this at z is equal to 0. And then here we have z squared plus y squared is equal to 1. And so that's going to give us the top part of our z limit. And then we'll say z is equal to 0 for the bottom part, and then we'll just take our volume and we'll double it. Okay? But what is important is to take a look at the view from the top, where we're just looking at the shadow of the xy plane. And so if we take a look at this drawing from the top, it's a circle. And that makes sense, right? Because that's one of the cylinders is going to be going straight up at you. And so that's the top view. So when we take a look at the top view, it's going to be just a circle of radius 1. And then if we look at that in terms of r and theta, we just see that r goes from 0 to 1, theta goes from 0 to 2 pi. So let's summarize what we have. We have a z set of limits going from 0 to the square root of 1 minus y squared if you take care of that. We have r going from 0 to 1 and theta going from 0 to 2 pi. And then, like we said, because we're going from 0 to the top part of this solid, we're really just looking at doubling it. So our actual volume is going to be twice as much as what we're going to compute. And remember that our integrand is going to be 1. So now when we do a triple integral in the appropriate coordinate system, our 1 is just going to be 1. Our dv is going to have an extra r. And then we integrate with respect to z first, going from 0 to the square root of 1 minus... Oh, we don't have any y's in cylindrical coordinates. What do we do? So y is equal to r sine theta, so I'll just replace y with that. Forgot to do that, sorry. And then our dr is going to go from 0 to 1, and our d theta is going to go from 0 to 2 pi. Now, unfortunately, we can't take any d thetas out like we've been doing before because there's a theta inside of the z. So really, this would be a good example where you need to integrate from inside out, one by one, variable by variable. So the integral of this thing with respect to z, there's no z's in there, so that's just going to be r with a z in it. And our z limits are going to go from 0 to this whole big thing. Right? And then we'll put this in for z. We're going to get r times the square root of 1 minus r squared sine squared theta dr d theta. And then this will require a u substitution, I believe. And we're going to want to integrate with respect to, or take the derivative with respect to r, treating theta as a constant. So the r here could kind of undo itself. And then we would have, what would we have? We would have negative 1/2 and then a sine squared theta. That's cosecant or something, isn't it? We'll deal with that later. And then we'll integrate u to the 1/2 power. So u to the 1/2, u to the 3/2 times 2/3. I'm keeping the r limits here because I'll change everything back into r. Probably should have canceled some of this. So I'll cancel the 2 and make this a 3, the 2/3. And then I have u, which is equal to 1 minus r squared sine squared theta to the 3/2. So if we put 1 in here, we're going to get 1 minus let's take the constant out. We got 1 over sine squared theta times, if we put 1 in here, we're going to get 1 minus sine squared theta to the 3/2. And then if we put 0 in there, we're just going to get 1 minus 0. Oh, that doesn't look so easy anymore. Yeah. Yeah, it's a cosine. I mean, this is a cosine, and we'll move that along. But I'm still looking for some easy shortcuts. All right, so this is a cosine, right? And then, so it's cosine cube theta. And then this is a cosecant. I think we have an integral for that, don't we? No, it's not cubed. Squared. Any of these things turn out to be easy? Sine over cosine, cosine, cotangent. It's cotangent, but these have different powers, so I'm trying to think ahead and see. Yeah. Say it again?
It might not work, but if you put all the one fraction of sine squared theta on the bottom, so cosine cube theta minus 1. I don't think
I don't know, because it's cubed. That's the hard part. Yeah.
Can you peel off one of those cosines and then just say that cosine over sine is cotangent squared times cosine?
Yeah.
You can
All right, let's break this up to two different integrals. We've got integral from 0 to 2 pi. Let's write this as cosine squared theta. I'm going to do a bunch of extra steps here. Sine squared theta times cosine theta. Actually, let me redo that. This is a cosine squared theta up on top. And I think if you do a u substitution here where u is equal to sine theta, you're going to get something that hopefully would be manageable. This is one of those not substitutions, but trigonometric integrals. If you have a sine or a cosine to an odd power, you want to take one of those sines or cosines out and then use identity to make a u substitution. And then this one is negative cotangent. Right? Derivative of tangent is secant squared. So (0 to 2 pi). Boy, I think I'm done with this. Should have just plugged it into Wolfram Alpha Mathematica. Well, anyways, this is how you would find the volume if you were to keep going. And like I said, this is a type of integral that won't show up on a test where you have to evaluate these things. Okay? So your integrals should just be basic. If you have to compute them, I think most of the time you'll just have to set them up. All right. We're reviewing for the test.
When is the test?
Monday. Yeah. Is this your trip? You already took your trip.
All right, that was done.
Oh, okay. Yeah, so we're just going to review.
Sorry, what did you talk? Sorry.
Oh, what I talked about last Thursday. Triple integrals. Yeah.
Professor,
Yeah.
I was just wondering, how many STEM paper series do you accept?
Up to 5.
Five?
Yeah. Uh-huh.